sponsored by InstaDeep, DeepMind, and Iconic. We are very happy today to have Ashley Edwards with us. Ashley has a very wide diverse of experience because he comes from the RL background to AI at DeepMind. She has worked in some of the papers presented in NICAL from previous speakers like Gato or Ginny, but she has moved now to Runway, where she's a member of the technical staff. So she has moved now more to world models. And I think today she's going to tell us more about how she made that transition from a full embodied RL background to these new future discoveries. So I think we're all very excited. So without any further ado, thank you for coming. We have networking session afterwards. If you are online, please type your questions on the Zoom link. We will, in the Zoom chat, we will read them out loud. Now, Ashley, floor is yours.
Awesome. Yeah, thank you so much for the introduction. Thank you for inviting me to be here. Thank you all for joining me today. So yeah, I'm really excited to talk about some of my work for how we can sort of learn structure from videos. In particular, I'll be talking about how we can learn actions and policies and rewards and even environments from videos alone. And so in the past year, we've seen a lot of progress in text to video, image to video generation. In fact, this slide here is kind of outdated, even though it's just from a year ago. So I think one thing that I want to talk about today is why is this interesting? And in particular, I'm interested in why is this interesting from an RL person standpoint? Because for non-RL people, I think it's kind of obvious, like video models can be used for things like film and advertisements, ideation. But I think one thing that becomes interesting if you're actually working with agents and coming from an RL field is that videos actually encompass a lot of the kind of information that we see in the world that we live in ourselves. And so if we can actually learn some things from these videos, then this is going to bring us closer and closer to more generalist agents of the future. So I guess the point that I want to make is that there's a lot more that we can learn from videos beyond just generation. So I would say a lot of the work that I've done, I wouldn't say it's inspired by this, but I think it can probably be encapsulated from a clip like this. So this is from the movie Chappie. And so in this movie, you have this robot that learns how to sort of mimic this cartoon character just by observation. And there's a lot of interesting things here. One is that it's able to learn very quickly just by watching this, how to perform this task. But also it's learning how to actually translate what it's seen in the video to its own embodiment, which is quite different from what it's seeing here. So basically during this talk, I want to discuss how we can actually learn sort of structures from our videos that could enable us to learn something like this. And so I'm going to be going back to some of my really old work and some of my more newish work, even though it's from a year ago, but I think it's already getting a little bit old. And the reason I wanted to sort of structure this way is because I think a lot of my more recent work was actually inspired by a lot of things that I did in the past. So I thought it would be nice to have some of that context. So if you're coming from a reinforcement learning background, you've probably seen this sort of figure on the right here, where you have an agent that's taking actions in its environment and it's trying to basically learn a policy to maximize its reward. And so what I want to talk about is how we can actually learn parts of this sort of MVP or agent environment interaction from videos alone. So very early on during my PhD, I would say I became already sort of frustrated with the reward function because I think a lot of us are probably familiar with the fact that you often have to come up with a reward to get your agent to solve some task. And every time you have a new environment, you're like, okay, well, darn, I'm going to have to come up with a whole new reward function. And so one thing that I became interested in, this is going to be the older work, is how we can actually start learning rewards and value functions from environments alone. And so this is what I'm going to talk about first. So I want to take you all back to the summer of 2016. So during this time, I had the opportunity to go to Japan to work on this robot that you see here on the left. And so this robot, it's actually quite interesting. So the name of it was Kobion. But it's like a comedian robot. So it was able to make gestures and like facial expressions. And when I came to Japan, I was thinking, okay, well, I was interested in teaching gestures or actually sign language back then. It was probably a very ambitious initial sort of PhD project, but that's what I thought I was going to be doing. But if you can see, there's like these gloves on the hands, and it turned out the hands weren't even working by the time I got there. So instead, I actually just worked on the facial expressions, because facial expressions are also an important part of American Sign Language. And so the robot was basically able to make a bunch of different facial expressions. And I wanted to actually use reinforcement learning to be able to train it to make different kinds of expressions. But the problem is, again, like, how do you come up with a reward function for training an agent to be able to learn in this way? So one thing I started thinking about is, well, I mean, humans can make facial expressions. Like, is there a way that we can actually take expressions that humans make and be able to translate it to the kind of expressions that this robot can make? The problem is, like, well, this is like a cartoon character. Like, how do we extract meaningful features from a human that will enable us to transfer it to the robot? So we started thinking about, like, what kind of representations can we use such that we can extract a reward function for training these agents. And so one thing we started looking at is something called a motion template. So this was some sort of pre-existing representation that basically shows you the shape of motion as well as when and time it took place. And I guess the nice thing about the motion template is it kind of extracts away the parts of the features of a human that would be difficult to compute a reward function from, and it just puts it into this sort of motion template space. And so we basically tried to compute these for both the human and the robot. And now you can see, so on the left, this is like the robot smiling and the human smiling, and on the right, it's like making a surprise face. You can start to see that these structures actually look kind of similar. And so once we got those sort of similar representations, what we can do is we can compute a reward function that said how similar are these representations. And we are able to actually, like, basically use these as our goals for the agent. So on the left, you see it kind of learning how to smile, and on the right, you see it like making a surprise face, kind of. This was a workshop paper, but I still think it's kind of relevant because this is when we first started thinking about like how we can learn this sort of structure from videos alone. All right, so I guess the takeaway from that initial work is that there is structure in videos that we can try to exploit and learn from. That work still required a lot of sort of manual tuning. So we had to extract like things like hog features and come up with this hand specified reward function. So after this, I started wondering, like, how can we maybe use more of these inductive biases to actually just learn directly from the videos themselves? Yeah. And let me know if there's questions. Feel free to like stop me along the way. I'm happy to take them. But this is like very early work, so I've forgotten some of the details. Cool. So that was learning rewards from videos. And the thing with learning rewards from videos is that you still have to train a reinforcement learning agent to learn from this. So after this work, we were kind of interested in, well, how can we maybe learn a value function? Because a value function actually already encompasses a lot about how you want to behave in the world. And then you can just use an agent or pass it along to an agent to try to maximize the value rather than the reward. But one thing we were thinking, so imagine you're like trying to solve some tasks. Like, let's say you have an IKEA table that you want to construct. It's often better to at least have the pieces out of the box than it is to have them within the box. And I would say it's even better to have the table constructed versus having the pieces on the table, unless, I mean, you might really enjoy constructing the table yourself, but in general, I think most of us would like the task to be completed. So imagine this for a video. We can sort of take this idea and apply this by assuming, let's say, that you might get a reward at the end of your video. So basically, you would say, I would get a reward once the task is complete. And then you can kind of just discount that further along towards the beginning of the video. So you say, okay, well, the other thing is a little bit less value, and in the beginning, it's a little bit less valuable as well. So we can construct a value function using this sort of idea.
May I ask you, how do you find the goal state, like in a reliable way? Like, because maybe if you change the light, you change the position of the camera, like.
Oh yeah. So the question was, how can you find the goal state in a reliable way? Because I guess the orientation or that sort of thing might change over time. I think the answer is scale. If you have enough data with enough sort of different orientations and that sort of thing, then hopefully how we were able to learn this value function. So again, imagine you have this rollout of states. What you can do is at any single state within your video frame, you can say, okay, this is this many steps away from the end. So I'm going to say this is the value discounted that much. And then you can learn this in a sort of supervised manner. So this video is basically showing what the value function learns. So we trained it over videos of like different pouring tasks, and this is an unseen pouring task. But you can see like as you pour the bottle, the value increases over time, which is quite useful. But you also want to be able to do something with this value function. So we also tried this with reinforcement learning. So the nice thing about learning a value function is that's basically what you're trying to do in reinforcement learning. You're learning to take actions that maximize this Q function, the value of taking an action in this given state. That's what a value function is. So we can essentially plug in our value function. So instead of having to do this sort of bootstrapping step where you're taking actions, you're learning this moving target. We can learn our values from our videos alone, and then just plug them into this sort of Bellman update equation. So we don't actually have to do that bootstrapping step. We also assume that all of our rewards are 0, except at the end, so we can get rid of the reward function. And now we're basically learning this sort of kind of like a supervised learning objective almost, where we're just trying to figure out which actions can I take that's going to maximize our value. Questions so far? Yeah.
I'm kind of curious. So in order to learn these value functions, you have video demonstrations of the process.
Yeah,
Do
exactly.
you have examples of successful and failed tasks? Because otherwise I can very much see the value function being always correlated with how far you are in the video.
Yeah, that's a good point. So a technique like this will only be able to learn basically what the expert shows you. And so if you see I guess negative demonstrations, it's going to also learn that negative behavior. Does that answer your question?
Yes, so there is this correlation between how far you are in the video demonstration and how high the value is.
Yeah. Yeah, but I guess the problem is like if for example you deviate from the path of the expert, then if you don't have a reward function, you're just gonna get lost. Yeah, but it's also similar like if you're familiar with behavioral cloning, like if you've only seen expert demonstrations, then it's going to be difficult to learn non-expert behavior. One fix for this would just be like assume you have some reward function, and then you also try to maximize that along with your values that you've been given.
Absolutely. No, my point was more, but I'm sure this is coming later on.
Yeah.
If we now have a bunch of videos of people doing stuff great and not so greatly, can we learn from all of them? Or do we have
Oh, yeah.
big next steps?
Oh yeah, we will be talking about how to learn optimal values later on. Yeah, but yeah, great question. Keep them coming. So yeah, basically what this is showing is after training, so this is coin run from OpenAI Gym. Yeah, the agent was able to solve tasks that it hadn't seen before using reinforcement learning. Cool, yeah, so this was some of my early work on how we can learn rewards and values, again, from videos alone. I guess one problem with this, though, is that you still have to like place the agent in the environment, and it still has to interact with this environment in order to actually maximize the reward. So the next work that we are interested in is how we can actually learn policies. So is it possible, just given a video alone, without ever placing the agent in the environment, can we learn policies that tell us how to maximize our values? So that's what we're going to be talking about today. So I actually wanted to go back to this sort of motion template representation. Because one thing that we were thinking is like these motion templates actually, I mean, this is showing us the behavior that we want an agent to do. And so one thing we started thinking is, well, would it be possible to actually generalize this to more tasks essentially? So we were looking again at this motion template representation. And so this was, I guess, one of the first times I started looking at training at scale. So we had this video game data set from archive.org, where basically they have like a collection of speed run videos where people like try to basically play video games. And what we were interested in is like, is there a way that you can extract behaviors from these videos, even though like these video games look, I mean, they look quite different, although there are some similarities across them. Like you have agents that are moving around in the scenes and like enemies that you're trying to avoid and that sort of thing. So again, we are interested in how we can use motion templates to extract behaviors. So you can see here, like if you look at these different images, you can see like where the character is and kind of how they're moving across time. And what we were thinking was that we can use this as goals for reinforcement learning agents. We never did it. This was another workshop paper, but that was the inspiration here. And so the way that we learned this was we're doing image-to-image translation, if y'all are familiar, where you take an initial image, and we had a pair with the motion template generation. Given like a few seconds of the video, we can compute this. And then we were just basically trying to train this model to say, given this image, generate the motion template. Make sense? Cool. So yeah, that's basically what we were trying to do here. And again, yeah, so this motion actually can kind of represent what a policy might look like that you would want your agent to try to maximize. Right. So this is showing some of the results from this work. So these were like unseen videos or images, I guess, in this case. And you can see it's kind of difficult, so I'll highlight some of them. But you can see like on the top, this is showing where the characters are. And on the bottom, you can see like how the characters are moving. It's a little bit difficult in this case to actually figure out what the agents are, which ones are the ones that you actually want to control. But this is actually in general a recurring theme in my work where it's like, how do I know if I'm controlling the agent or the physics in the world? But you do see that it's able to actually extract out the characters here. And you see that in this case as well. We also found that work, even though we had only trained on video games, that we could actually use it to sort of segment out animals, even though we had not trained on this kind of data set. And this was like, I guess, sort of emergent behavior of this work, where I guess you trained, again, at some sort of scale. I think it was like 100,000 images that we trained on. But we were able to actually generalize to unseen videos, which we thought was kind of cool. Okay. So I guess one problem with doing the sort of next frame prediction, which we were doing in this case, is that you can imagine that the sort of future predictions, especially if you're training using like a mean squared error, the future predictions are going to get blurred together. So it might be difficult, for example, to be able to tell, am I moving to the left, or should I be moving to the right, or should I be jumping in the air? So they kind of get merged together in your predictions. So instead of just predicting a single next frame, we started thinking about, well, how can I actually try to predict a distribution over my future? And this is when we start getting a little bit world model-esque. So you can see here, basically, that it's able to like predict moving to the rightish and moving to the leftish and like jumping in the air. But basically the way that we trained this was, instead of having a generative model that only conditioned on the state, we also conditioned on this Z here, that's basically saying, I want to look at all of my next predictions given a single initial frame, and I want to find the one that's closest to the actual prediction or the actual next state that I found. And I'm just going to minimize the distance between those. And essentially what I'm trying to do is say, okay, I'm going to kind of like cluster over the future. And this is learning all the different kinds of behaviors that I can have in given a single initial state. Does that make sense? Or questions? Cool. So again, as I mentioned before, we're finding that there is structure in videos that can be exploited. That work was getting a little bit more general. And what we found is that we can actually sort of learn these actions, represented in that case from motion templates, by just having a few sort of inductive biases. So now the question is, how can we actually train agents from this sort of from these sorts of ideas? So that was the idea behind our next work, where we're going to be trying now to actually learn policies from videos themselves. So imagine you're like playing a new game that you've never seen before, but you have this friend that sort of knows how to play the game. So by watching them, you can kind of figure out like, okay, this is how I can avoid characters or I guess enemies in the scene, or like these are the kind of obstacles I need to avoid, and this is the goal I need to reach. And you can learn this just by watching your friend. And then essentially what you need to do is once you take the controller, you just need to figure out, well, how do I actually take actions in the world that are going to enable me to actually solve this task? And so that was the idea behind our work, imitating latent policies from observation. So what we're going to do here is we're going to be given a sequence of observations, and we're going to essentially try to learn what we call a latent policy. Like, again, we're going to try to watch our friend essentially, or watch this video and figure out what is the task, what are the actions that I should take, even though I don't actually know the actions yet. And then after that, I'm going to take some steps in the environment to try to align these latent actions to the real kinds of actions that we can take in the world. So we're first going to talk about how we can actually learn this latent policy. So imagine you start from initial state like this. So we're going to use coin run again in our examples. So you might see a transition that looks like moving to the right, as well as a transition that looks like jumping in the air. Now, you're observing a video. You don't actually know what these actions are called. But the idea is we're going to define Z as being a latent action that calls one of these transitions to occur. So we don't know the action names. We know it's something hidden within the structure of our videos. And so we're going to also try to learn a latent policy that tells us the likelihood of taking one of these latent actions in any of these given initial frames. Okay, so this is how this is going to work. So let's say that we've observed this sort of next state transition in one of our videos from an expert. So right now we're assuming, again, we have expert data. So we might see a frame that says basically the agent moved to the right in this case. We're again going to be learning this generative model that's going to try to predict every possible next frame given my current states and this latent action, which we don't know yet, but we're trying to learn. So this model is going to try to predict every possible next frame. And then what we're going to do is, again, we're going to say, okay, given all of my predictions, I want to find the one that looks the closest to my ground truth next frame. And then I'm going to try to minimize the distance between those two. So I'm, again, sort of clustering over all of the future next states that I can have. And so we're, again, seeing the sort of same loss that we saw before in the previous work, where we're going to look at all of our next future predictions and try to minimize the distance between those and my ground truth prediction. Questions? Make sense? Yeah.
It's also trying to generate a state given some sort of latent space, and it does some sort of loss function fine.
Yeah, that's a good question. So the question was, how is this different from like the dreamer works, and I guess in general, like maybe world model works or that sort of thing. But the idea here is that we're assuming that we don't have access to actions. So those kind of works, you have like experiences and rollouts. So say this in this state, this is the real action that was taken. But in this work, we're actually trying to learn this from videos alone when we don't actually have access to actions. So we're trying to basically learn the future next states and learn a policy over those future next states without ground truth actions. Yeah. Question? Yeah.
Yeah. So I'm not trying to understand how you learn the action specifically. So do you have like a difference basically, or your model is a different possibility, kind of like mask model way?
Yeah.
You know, like if this one looks closer video, then I minimize this one and leaving the other ones alone.
Yeah.
Like this.
Yeah, that's exactly right. Yeah, so the question is, how exactly are we learning these actions? And the idea is exactly what you said. So we have this generative model and we're conditioning on the latent actions. I haven't talked about how we learn the policy yet, but let's just say we're assuming that we have, let's say, 3 latent actions in this case. We condition our model on each of these things to generate different next future predictions. And then I'm just going to take the one that's closest in some latent space, or actually I think we did pixel space in this case. Latent space is probably better. But yeah, we're going to try to minimize the distance between our generated next state and the ground truth next state, essentially. And so we want to, basically the model is going to try to predict all of these next things because it's beneficial to actually learn all of the different modes of our expert here. Yeah.
And how do you set how many latent actions? Is it just a hyperparameter that you just decide like?
Yeah.
Okay, and I assume that would affect how good you're learning.
Yeah, that's a good point. So yeah, essentially the number of latent actions that we learn over is going to be an inductive bias that I mean, a hyperparameter, I guess, that we're going to set. So I guess there's a few benefits to learning, I guess, less and more. So imagine like your expert only ever moves to the right, or maybe sometimes jumps. Even if you know that there's more actions in the world, you might say, okay, I'm going to learn a latent action space with just 2 actions because that's all my expert did. Or if you learn more actions, you might be able to capture some things about the physics that the model can't distinguish between like actual actions, like, I don't know, maybe like if you have other characters in the world and if you have a giant action space, you might be able to control the characters, or maybe even gianter, you can control both the characters and the agent and the enemies and that sort of thing. But yeah, it's definitely something you have. Yeah.
Sorry, maybe you will explain later on, but from this formula, it's not very clear for me what is exactly J and why it's not ignoring this.
Yeah. So G here is just going to be some sort of generative model that's predicting. So given a frame, it's predicting the next frame, second neural network. And the reason it's not conditioning or it's not ignoring Z is because it's going to be beneficial for it to learn all the different modes, essentially, because its loss is encouraging it to minimize the distance between the ground truth next frame and the predicted next frame. So if it were ignoring Z, it would essentially learn the expectation. So it'll learn the expected state and essentially blur over all of the next future frames. But by conditioning on Z, you're able to actually learn the different modes of a distribution. Does that make sense? Hopefully, maybe in the next phase, it'll make more sense. But yeah, sorry. Any follow-up or maybe?
Yeah, if you extend it a little bit more, like.
Let's see. All right, yeah.
How are you evaluating if like the latent actions close real actions, except for like doing quantitative comparisons? Okay, this latent action is like left or right. Is there any more like for better formulation of the problem in terms of metric that you can take or?
Yeah, I mean, the only way that we actually measured how good the latent actions were just rolling out a policy, essentially. But I think there's other ways you can maybe compare like if you have ground truth actions, you can compare the distribution of the ground truth actions to the latent actions, perhaps. But yeah, essentially just rolling out a policy. Cool. Oh yeah, I think I'll move on for now. So okay, so now I guess in this next part, we're going to talk about how we learn the policy, and maybe that'll make more sense how we're actually learning the generative model as well. But okay, so imagine, so on the left, what we're seeing is perhaps the distribution that we might see from an expert. So let's say given an initial state ST, that the expert moves to the right, like half the time jumps in the air, half the time stays still, never. And so the way that we're going to try to learn our latent policy is that we're going to essentially try to learn exactly that distribution. So if you were to take an average over all of those next frame predictions, or next frame coming from the expert, you might see this sort of, I guess, expected next states. And so what we're going to try to do is learn a policy that will enable us to weight all of our next frame predictions such that under that distribution, it would end up looking like our expected next state there. So you might say, okay, I want my latent action to assign half the time for latent action 0 and 0% for latent action 1, etc. Such that if you were to take the weighted sum under that, you would get something that essentially looked like the expected next state that was coming from our expert. And so that's basically how we're going to be training our latent policy. So we're trying to train it to learn how to weight all of these different futures similarly to how they're weighted in our actual expert data. And we can essentially compute the expected next state by weighting those by our latent policy and having a loss on our ground truth next frame and our expected next frame. Questions here?
You mentioned at the beginning that sometimes it was difficult for these kind of models to distinguish something that was an action from the expert from the physics, like for instance, you're polling. Does it affect in this part?
So in this case, we were only learning in environments where you didn't have to disentangle the physics from the yeah, but that's a good question. This work wouldn't be able to distinguish between physics and agents essentially. Yeah, but if you had a big action space and you can learn both, you can move the clouds in the sky if you like. Go for it. Yeah. Okay, so that was how we learned the latent policy. And essentially now, once we've learned our latent policy, we're going to have to take a few steps in the environment to actually learn the latent actions or align the latent actions that we've taken to the real actions that we can take in the world. So that's basically what's happening in this step. And I guess, yeah, just to give some more, I guess, a little bit more intuition here. So it's again going back to like, imagine our friend has played a game. We've maybe never picking up a controller, but we've figured out how the game is played by watching them. And now we know the policy. So all we have to do is take the controller, figure out what button X does. And once we figure out that that means jump, we can just move to the right or whatever. We can basically play the game because we already know how to play it from our previous step. So the way that this part is going to work is we're going to take some environment samples. So now we're actually placing the agent in the world and actually rolling it out. So we can say, okay, let's say in this state, you take action A, you end up in this next state here. The way that we're going to try to learn to map our actions, our real actions to our latent actions is, again, we're going to plug in our latent actions into this generative model to predict all of the different possible next frames that we can see. And then we're just going to say, okay, well, when I took this action in this state, this is basically corresponding to, or it's closest to this latent action. So that action is probably actually latent action 1. And so we're going to try to basically learn a function that can predict that using, again, the similarity between these two things. And yeah, that's basically how we learn to map these latent actions to the real ones that we can take in the world. Yeah. And so after we are able to learn this mapping, essentially we can solve a task after just interacting with it after like 200 steps, because we've already learned the policy. And so all we have to do is figure out how to map the latent actions to the real ones that we can take in the world. So yeah, oh yeah, question?
Yeah, is that a way to learn like continuous act?
Oh, that's funny. I was just having a conversation earlier about how we can do this. It's quite difficult, I think, in this case, because our actions. Yeah, exactly. In that case, it will be, I think the way that we're doing the mapping would be a little bit tricky here. But I think there's probably ways. I don't know how to do it yet, or I haven't really thought about how to do it. But yeah, good question. I think I've seen some works that are just like, look at the next, try to look at the next frame and like minimize the distance, or use those as a policy or something, and like maybe learn an inverse dynamics model, like over the ground truth environment states, I guess. Or you can probably discretize your continuous action space, but I never tried those ways. Yeah. Cool. Right, okay, so in that work, we are just interested in how we can learn policies from videos alone. That work was assuming that we had expert data, so we can really only be as good as the expert. And so in the next work, we were interested in how we can actually learn optimal policies from videos alone. Grab some water real quick. All righty. So yeah, I'm glad we've had some questions about this. But imagine essentially you have some demonstrations where your expert actually, or it's not really an expert, your demonstrator doesn't really know what they're doing. You know, maybe sometimes they happen to reach the goal, but oftentimes they actually fail at solving the task. And so in this work, we're interested in how we can learn from data like this, where we have a mixture of some good things happening, but a lot of bad things happening in our demonstrations, essentially. So I want to go back to this diagram. So again, imagine we have this agent that's interacting with this environment and trying to maximize its long-term expected return by learning a policy. The problem when you're learning from videos is that you don't actually have access to the actions. And so in this work, we're trying to figure out, well, can we still learn this optimal policy just from the videos themselves? And so basically what we do is, instead of assuming that you're learning a function that says in this state, take this action that's going to maximize my long-term expected value. Instead, I'm going to say in this state, how can you transition to another state that's going to maximize my long-term expected value? And we can learn this sort of function from the videos alone. So this is what we're going to essentially learn here. So a value, basically state next state value rather than state action value. And we're also going to be learning a policy over states that says, again, in the state, which state should I transition to that's going to maximize my value here. The benefit of this work is that, again, we're not going to require any actions for this initial phase. We're, again, going to have to map our policy to real world actions eventually. But we can actually learn the policy from videos alone. So we can do that completely offline to learn an optimal value. We're going to assume that we need a reward function. In this case, we can't really get rid of it. So basically, this is how this is going to work here. So again, we're going to be learning next state values. So that says, what is the reward for, or what is the expected return for moving to a state that's going to maximize my value here. And then we're going to be learning a policy over states, essentially. So this is what our policy might look like. For example, imagine that we actually know all of our future next states. We say, given my Q function, what is the value for taking the state that's going to maximize my value? One nice thing here is like in our update function, we also see that max is also there. So rather than assuming that we actually need to know all of our future next states, we can actually just plug in this policy function here. So if you're familiar with like TD3 or DDPG or these kind of works that are maximizing values in this way, you can essentially say, what is my reward plus my discounted value if I plug in my value, which is maximizing my future expected return, or that's what it's being trained to do essentially here. I realize I'm moving fast, so feel free to also stop me if there are questions on this phase as well. But also the way that we're going to be learning, oh yeah, sorry, you can plug that in here as well. But yeah, so this function here is actually going to be, going to be able to train this in a similar way that we would train most like deep reinforcement learning functions, but we're using our policy over states rather than a policy that says what action I should take. And then the way that we're going to be training this policy is essentially going to say, I want you to maximize this Q function. So it's basically similar to what you've seen, except we're now having a policy over states rather than over states and actions here. And then again, in order to sort of map our actions, our policy to the actions that we could take in the real world, we're now going to be learning an inverse dynamics model that's going to say, given this state and next state, tell me which action was taken. And so when my policy says take this action in this state, or sorry, move to this state, given my current state, we can plug it into our inverse dynamics model to extract the action that we need to take. So that's what's happening here. Yep.
So when you have actions go from basically a state to the next state, how do you determine which next states are also available from the current state?
So oh yeah. Yeah, so basically this work is going to be learned offline from our videos alone. And so we're assuming we have next state pairs that we've seen in the data. So we say, this is basically given the state and next state, I got this reward, and then I can basically compute it this way. So we're assuming that we're not rolling the agent out yet in this case. We're learning directly from the video data. Yeah. Other questions? All right, and yeah, we can basically sort of learn this inverse dynamics model by having a supervised loss and ground truth state next state pairs. Cool. So this is essentially showing like if we are given some random rollout, so we did this in, I think, Reacher is this called, an inverted pendulum. So this is showing actually suboptimal data. And so usually, again, if you're given suboptimal data like this, it'll be very difficult for you to learn from videos like this. And here what we see is that we're actually, so this is showing the actual policies that we rolled out. So this is our policy over states now. And you can see that it's learned to actually balance this pendulum here and like reach towards the ball thingy, even though we are only given this sort of very suboptimal data. Yeah.
Just the reach
state is just the video.
Oh yeah. In this case, we actually didn't do it over pixels. So it's actually the like joint angles and yeah, that was a good question. Yeah. Other questions? Cool. And so yeah, so basically what this table is showing is that as we get like more and more random data, our approach is able to outperform like behavioral cloning from observation, which is, I mean, it's a behavioral cloning approach, so they do as well as the expert. And one interesting thing was actually like we found that our approach didn't work well with like completely, or sorry, it didn't work well with completely expert data. So we actually needed some randomness injected into the environment. But one reason might be because we're actually learning, we need to have some sort of spread over the actual environments here. So you see like at 0, we actually do worse, but as we add a bit of randomness, we're able to perform better than the previous state of the art at the time. Yeah. Cool. Yeah, so basically in this work, we were interested again in how we can learn policies from videos alone. And this is beneficial because once we learn those policies, we can very quickly just figure out how to take actions in the world. So I guess the last thing to figure out is how we can learn environments themselves. So this is, I guess, my most recent work. So I actually want to take all back again to, I guess these are some of the old school from these kinds of environments. You're not going to get any sorts of generalization. So this is like, I guess, very, very early on in reinforcement learning days, the kinds of environments that we were training over. And nowadays, of course, we have a bit of benefit of scale in terms of environments. So this is showing like Atari and some robotics tasks that we can learn over. And this was one of the ideas behind the work Gato, where you're essentially trying to figure out how can I learn over a bunch of different, given a bunch of different environments, how can I learn policies? The problem with trying to scale just from environments alone, though, is that, I mean, you still have to kind of get the environments, and every time you have a new environment, you're going to have to sort of onboard it. And I think the problem is it's very difficult to actually really scale the like ground truth environments that you have. So basically the idea behind our work Genie was that we wanted to see if we can actually learn environments from videos alone rather than actually having to use real world environments. And so in this work, we're trying to learn the sort of generative interactive environment purely from videos that's playable by both humans and AI agents. So given videos from the internet, what we're trying to do is now we're trying to learn a world model that says, given this frame, an unseen frame, a generated frame from text and that sort of thing, I want to be able to condition on an action even though I don't have actions. And I want to be able to essentially predict all of the future next frames such that I can interact with its environment like it were a real game, or I can give it to an agent and that agent can interact with it like it were a real environment. So this is basically what our architecture looks like. So again, we're going to be training over, and this is another one of these large scale things. We had 30,000 hours or so of videos, data that we were training with. But let's say we have some frames. What we want to do again is try to learn a world model. So we essentially have this video tokenizer that's going to be our representation for our videos. We're again going to have this latent action model that's going to be trying to infer actions from videos, because again, we're assuming we don't have any ground truth actions. And then we have this dynamics model that's going to be taking our video tokens as well as the latent actions and trying to predict the next future frames. Questions? And I'll go into each of these different components as well. So basically the way that the video tokenizer works, and we're going to be learning this before we actually train our model, but we're essentially going to be taking in video data. We're going to be using something called a VQVAE to tokenize this, and then we're going to be reconstructing that. And so we're learning embeddings or tokens that represent our video data such that if we give that to a transformer or something, we can actually predict the next tokens. And again, we're going to be now learning a latent action model, but we're actually going to be doing it quite differently than we did in this previous work, where we're actually trying to say, given my frame, I want you to predict all of the future next frames. Because you can imagine if you have maybe 11 billion parameter model, that's going to be quite inefficient to actually have to predict all of the future next frames. Instead, what we do is we try to learn this latent inverse dynamics model that says, given my previous frames and a single next frame, I want you to compress these in such a way such that if I take that sort of compressed latent action in my previous frames, I can use that to predict the next frame. And so essentially what we do is we place our previous frames and our next frame into this bottleneck, plug that into, again, the VQVAE, which is enabling us to discretize this space. And then we can take that latent representation along with our previous frames and predict the next frames. Does that make sense? Yeah.
Is the next frame available to be encoded? Maybe the encoder finally find a way to simply cheat and output the correct values next frame.
Yeah.
The encoder doesn't learn it.
Yeah, that's a good question. So it's the question is the next frame also available to the encoder? Because then it might be able to cheat in order to predict the next frame. Thing is, we want it to cheat, but only a little bit. So essentially what we do is we compress these. So we place it through this bottleneck with, like, let's say we have like maybe 8 discrete actions and the embedding size of it is 32. So you're given like pixels. So it'd be very difficult to have all the information about the next frame within an embedding size of 32 or whatever. But the idea is that we just want it to be able to extract enough information such that it can predict the next frame. And that's what actions are. So it's saying, okay, in this embedding, I'm going to encode moving to the right or moving to the left or et cetera. But if we didn't place it through that bottleneck, then yes, it would likely be able to cheat in that way. Like if our embedding size was the size of the pixel space, then it would definitely be able to cheat. But we're compressing it.
And then at runtime, you also use next frame for encode for the latent or previous frame.
Oh yeah, good question. I'm going to talk about inference next, but I guess the idea is that we don't have the next frame during inference time, so we can't actually give it to that. What we do is we give it the latent actions. Other questions? Cool. Yeah. So I'm sorry, in the next time we're going to talk about inference. This is actually talking about our dynamics model. So basically, so we actually discard this decoder here. It's a weak decoder. We're just using this for training the latent actions. And then our more powerful dynamics model is going to be a transformer. You might be asking, well, why didn't you just use a transformer in this phase? And the reason is it didn't really work at the time. It would be more elegant to actually use it, but I think this worked better by having in this sort of two-phase step. But essentially what we can do is given a video, we tokenize that using our video tokenizer. We take the inferred latent actions using our latent action model, and then we plug it into this dynamics model that's being trained to predict the next frame tokens. And in this case, we're using a technique known as mass skits rather than diffusion. I think nowadays diffusion probably makes more sense, but that was what we used at the time. Questions? Yeah.
So I'd like to understand the difference between the dynamics model and the next frame predictor.
Yeah, good question. So basically this lamb decoder here, so that was the one that was doing the next frame predictions, was trained using a mean squared error, and the results were quite blurry. And we found that it was easier to use this sort of representation for training our latent actions. We could try, we did try to use the transformer model to train our latent actions, but we found that was much harder to train. But they are essentially doing the same things with different kinds of losses. Like this was trained with mean squared error. The other one was trained using cross entropy loss over the next tokens. And that gives us the sharpness that we need. This gave us the latent actions essentially. But yeah, it would be better if they were basically the same. Yeah. Cool. Any other questions? Great. Oops, sorry. And this is essentially here showing what happens at inference time. So I guess one of the benefits of Genie was that like we trained over lots of different videos. And so we can be given a new unseen image essentially and interact with it like there were a real environment. So what we do is we take an image that someone has created, like maybe from a text to image model, plug it into our model to get our tokens. And then we can take a user action because we're actually discretizing our action space. We can say, okay, the user said take action 0. We can plug that into our model to get the next frame, and then we can basically interact with it in this way. So we take that next frame, plug it back into our model, take an action, and figure it out. The cool thing here is that like, you might be wondering, well, how do you know what the actions are? But it's like similar to kind of the other works that where the agents needed to figure out the mapping. Like in this case, I guess a person needs to figure out like, oh, this is in action 0 means move to the left. I'm going to have to like fumble around a bit, but eventually you figure out how to interact with the models. We also found that Genie benefits from scale. So we were able to find that we can scale the batch size as well as the number of parameters, and it scaled gracefully, and we were able to get our final like 11 billion parameter model here. Okay, so this is old. I mean, it's from like a year ago, but now it's old, but whatever. So this is like essentially showing what the results look like. So these environments were all generated from our model. This is actually showing the team stepping into these environments and interacting with them like your game. So what you can do is take a text prompt and say, I want you to generate this image that's separate from our model, and then we can plug that into our model and essentially play it. So these were all like Genie generated games. After I left DeepMind, they released Genie 2, which I mean, the results there are so much more impressive, and it's over 3D environments, but that was like after my time. So this is what we see. But yeah. So I guess one thing that we wanted to see is that like how consistent are the agents and how are the environments and actions, and also how diverse are the trajectories that we learn. So what we're seeing here is like, given the same initial frame, if we plug in different latent action sequences, we get like these different diverse trajectories as shown here. So you actually are getting this sort of world model environment as shown here. And also we found that they're consistent, because it's one thing to be able to actually learn latent actions, but if the meaning changes given different initial images, then they're not really that useful. But you can see here on the left that you're able to, if you plug in the same sequence of latent actions given different initial scenes, that you get similar trajectories, which also indicates that the actions are consistent. And we're again able to learn this in a completely unsupervised way without using any ground truth actions or object detection or NERF or key point detections or poses or anything like that, all from videos alone. So I think one of the fun things that we found was after we were able to actually get this initial model, we realized that we didn't actually just have to use text to image models. We can also like sort of play sketches. So for example, on the left, we have like a sketch from Richie, and in the middle, one of Jeff Kloon's kids made this sort of sketch here, and on the right is my thingy, but don't judge me too much. And we found that we're actually able to like, I mean, you can climb Richie's drawn ladder here, and the little football player moves to the right, and my little whatever blob thingy there is jumping over the platforms, which we found was like quite exciting. And it also worked on real world images, even though we'd only ever trained on video games. So yeah, that's Jack's dog Doris and my pizza and Jim's figurine thingy and Jake's other figurine thingy, I think. And yeah, we're able to basically, again, like move these things around, even though we had never actually trained on this sort of data. So this is like an emergent behavior that we found. A question?
Once you sort of get out of the image,
Oh yeah.
does it become blurry, or does it generate pretty?
Yeah, so the question is what happens once you get out of this initial scene. I wouldn't say it becomes blurry, it just becomes very uninteresting. So I think the first initial frames were, I mean, they're kind of interesting. You can like jump and that sort of thing. I think this was one of the problems, like, or I guess it was coming from the technique we used, like, which was mass skits, but I think diffusion might give you a little bit more interesting trajectories. And yeah, other questions? This also worked on robotics data. So we trained a different model using the same hyperparameters and everything, but we just wanted to see if it actually worked on robotics data, even though we had the action data there, but we didn't use it. And again, you see if you plug in the same trajectory across different initial scenes, you get similar sort of motions. And And so this was another indication that our model was general. Nothing was saying that we had to learn from game data. It was just sort of convenient and also fun to try to learn from that sort of data. And finally, so again, we were interested in seeing if we can use this sort of model for training agents. And so we looked again at doing behavioral coding. So the way that we did this was we took one of our models that was trained on the internet, extracted the latent actions from those, and then tried to see if we can use that to label unseen videos and then learn a policy. And so we were able to find that we were actually able to train agents using this sort of technique. So yeah, if people are interested in reproducing this, I think there's also open source repositories out there now, but we also have, ways to also reproduce this within the paper in the CoinRun environment. So yeah, that's basically all I have. But yeah, I guess hopefully I've shown that we can actually learn a lot just from videos alone, and these videos contain a lot of the structure that we already need in the world. We just need to figure out how to best extract it. And so on the right, actually, we can see this is Runway's camera control model. And you can see you can actually already control these videos just using camera controls. So I think in general, I'm just interested in how we can get better controllability in our video models. So yeah, thanks. That's all I have. Thanks for your time.
Any last minute questions?
Oh, sorry. You go ahead. Yeah.
For this example in particular, camera control, would you still have discrete actions?
So in this case, it's continuous. I think you can draw on the scene and it like move the camera around.
But the previous example showed discrete actions, right?
Oh yeah. The previous example, sorry, was discrete. Yeah, sorry, we had a question in the back first. Yeah.
Thank you for the presentation. It was really impressive. I wanted to understand, like, how do you generalization in this case, in these cases in general? Because first of all, do you?
Sorry, I can't actually hear exactly what you're saying.
Sorry, I was asking, like, how do you actually handle the problem of goal misgeneralization in these cases? When you just have like the video, and specifically when you were talking about that you have like not the correct training data in general, like sometimes let's say that the entire training data was kind of biased. Let's say that the game player had all the goal points towards the right of the screen, and then now let's say the environment changed, and in scenarios it might not perform the way that was able to earlier. So I just want to understand.
Yeah. I mean, so in the case of Genie, I think it was better to learn from suboptimal data in that case, because we're not learning a policy apart from the previous part I just showed, but we're learning a world model. So we actually want to learn all the different trajectories. So in that case, it wasn't necessarily about trying to learn the most expected policy, but rather how can we learn to generate environments that encompass basically anything that can happen in the world. If you are learning a policy, then I think it's very difficult to actually learn just from observation, see expert data if you don't have a reward function. But if you have a reward function, then yes, you could try to maximize that. I think we had a question here first. Yeah.
So I was wondering here, I guess you're using some recirculated watching vendor like actions. How does this compare to just camera control, just using nerves?
So I think the benefit of our work here is that you can essentially learn the latent actions without any inductive biases, and you don't necessarily need information about the camera pose and that sort of thing. But the other thing is that you actually are able to have dynamic scenes here. So you have like things moving in the background, and I think nerves basically enable you to maybe look around a scene, but you don't typically see like dynamic characters. Does that make sense? Yeah. I think you had a question, and then yeah.
Yes. So basically, like you said, like the expert data of 0% to 100%. Is this coming from like PPO agent or something like this, or how do you define like expert vs no expert data?
Oh yeah. So basically, what we did was we just every percentage of the time we randomly took a different kinds of action essentially. So we randomly sampled like not the expert action. Does that make sense?
Yeah, but the expert action was considered something that was coming from PPO agent or like,
oh yeah.
Like,
yeah, exactly. Our experts were reinforcement learning agents. Yeah, that's a good point. yeah, yeah.
With like these high detail, like 3D world models, you need to like scale the action vocabulary that makes that set the two, in case of like two games, which is too small, then like continuous actions, yeah, scale that as well.
Oh yeah. So like in the case of robotics, we also, I think it was either 8 or 10. I don't actually remember how many actions we had, but we didn't actually scale to that. But I think I mean, it would benefit probably in these sorts of cases if you had larger action spaces. For video games, we also just had like 8 or 10 actions.
It's just zero shot from model that's trained from video games to get to like post-train robotics.
Yeah, so this was a separately trained model, so we didn't use a game model, but we used the same hyperparameters, and like we basically said, okay, this is 11 billion or however many billion parameters with, I don't think it was 11 billion, but I don't remember how many, however many billion parameters with this bat size, and yeah.
I'll also like hypothetically, if I have a really good pre-trained 3D world model for robotics, but then I want to post-train it on stuff that I have action labels for, is that possible?
Oh yeah, that's actually a good idea. Just plug them in. I think in our
Change like training architecture, because I need to feed the action labels and stuff.
I mean, I imagine you can do some sort of regression with your latent actions and like try to get them to correspond to the ones you've seen in your data, but you'll probably have to change something. Yeah. Sorry, I don't remember. I guess yeah.
I have a question about the latent action model. Like if you use to pick the next state, like as I understand before, we use this latent action model to learn distribution of action and not expectation of action. But like if you use generic one like diffusion learning distribution well, like do you need this second model, or you can use a latent action of the model, because like the traditional autoencoder or diffusion anyway used like latent representation, and you don't need the second model.
I think the main benefit of having, I guess, the latent action model is that you get controllability. So in a diffusion model, you might say, okay, generate me a video of someone walking down the street, but you're not going to be able to step in and control it to say, okay, move. I want this person to move to the left. It's learning to predict this next frame, but it's not very easy to actually control what that next frame is doing. Does that make sense?
Okay.
Yeah.
Okay, so here we're running a bit over time.
Yeah.
So very quickly for those of you in person, we're gonna have you want to say something about?
Oh no, I just wanted to thank my collaborators as well. Yeah, yes, please. Yeah.
So I was going to say, for those of us in person, we're gonna have some food now. You can make some extra questions to Ashley. Our next session will be in May. For those of you on YouTube, we encourage you to subscribe, but it won't be online. The speaker is coming from New Zealand, so really you don't have an excuse not to attend to this one in person. He's a double Oscar winner. He was in the movies of Avatar and King Kong. He has been doing animation with neuroscience for the Avatars and the Kong. And he has a lot of very diverse background. He has been keynote speaker into a lot of very big conferences. So it will be a lot of interesting stuff that he can only show if we go offline. So I strongly encourage you to come. In person will be, I think, the 21st of May, but we will post it on X, on YouTube, Eventbrite. No, YouTube no, on Eventbrite and all our social media. So we encourage you to keep an eye on that, because we expect that the tickets to go fast. Thank you all for coming, and I think we can give another big applause to Ashley. Thank you very much for coming today.